The German mathematician Carl Friedrich Gauss once said, "Mathematics is the queen of sciences and number theory is the queen of mathematics." So let us learn few more topics from number theory. Here we go for theory of congruences. So far we were looking at the divisibility questions through their devices. We are looking at what is the greatest common divisor of two integers, what is LCM, and we are looking at the prime factorization and all. Now we are approaching the divisibility question through their reminders. And this approach is nothing but theory of congruences, which was first introduced by Gauss. If a number n measures to be the difference between two integers a and b, then we say a and b are congruent to each other with respect to n. Otherwise, we say they are incongruent. Okay, putting this in the form of definition, let n be a fixed positive integer and two integers a and b are said to be congruent modulo n. That is written as a congruent to b mod n. We write it like this. If n divides the difference a minus b, divides the difference a minus b, provided a minus b is equal to k times n for some integer k. For some integer k, we write a congruent to b mod n, where n is a positive fixed positive integer. A and b can be any integer. We say a congruent to b mod n if n divides a minus b, in the sense a minus b equal to kn for some integer k. Note that two integers are congruent modulo n, modulo 1, but whereas two integers are congruent modulo 2 when they both are even or both are odd. So usual practice is to assume that this n is greater than 1. Got the point? Two integers are congruent to modulo 1, it is common, but it is congruent to modulo 2 if both these are even or both of them are odd. So usual practice is to consider this n as greater than 1. Let us look at the important theorem. Theorem says, for an arbitrary integers a and b, a is congruent to b mod n if and only if a and b use the same non-negative remainder when divided by n. Let us prove this. Let a is congruent to b mod n. Usually we put the bracket, sometimes I forget to put. Okay, let a is congruent to b mod n. Then I can write a equal to b plus some k times n. Okay, for some integer k. Upon division by n, b leaves the remainder r. Okay. After dividing by n, b leaves the remainder. I'll take it as r. That is, I'm writing b as qn plus r. Okay. Then this is same as writing now. I can write A is B plus Kn. I'm rewriting A by substituting B as Qn plus R. Qn plus R plus Kn. This is same as writing Q plus K into N plus R. Now even A is giving me the reminder as R. This is also an integer, right? So when n divides A, it is also giving me the reminder as R. So which indicates that A has the same reminder as of B. Okay, so they are giving you the same reminder. Now the thing is, I have to take up the other way around. If they are giving you the same reminder, whether A is congruent to B or not, that we have to check. Okay, so on the other hand, suppose A equal to Q1 plus R. A is also giving the reminder which is same as B. Okay, Q2n plus R. Reminders are same. It's the same reminder in such a way that 0 less than or equal to R less than n. Here I have forgot to mention this. Here when you write it like this, no, this reminder should be greater than or equal to 0 and it should be less than n. So now A and B are giving the same reminder, that is R. Then I'll write A minus B, which is nothing but Q1n plus R minus Q2n plus R, which is nothing but Q1 plus Q2 into n. This R will get cancelled with this negative R. Okay, so what does it imply? It means n divides A minus B, which in turn implies A is congruent to B mod n. Hence the proof. Now let us study few properties of congruences. If n is any positive integer greater than 1, which is fixed, and a, b, c, d are the arbitrary integers, then first property says an integer is congruent to itself mod n. A is congruent to A mod n. How? See, I can write A minus A as 0. This is same as writing A minus A equal to 0 into n. What does it imply? It implies A is congruent to A mod n. Right? So, integer is congruent to itself modulo n. Second property says if A is congruent to B mod n, then B is congruent to A mod n. If A is congruent to B mod n, then I can write A minus B equal to K into n for some integer K, right? So I can write B minus A as minus Kn, which is same as writing minus K into n. Since minus K is also an integer, I can write B is congruent to A mod n. This is the second property. And the third property says if A is congruent to B mod n, and B is congruent to C mod n. Then it says A is congruent to C mod n. Let us see how it is. See, it says A is congruent to B mod n. Therefore, I can write for some k I can write A minus B equal to kn, and for some h I can write some integer h, B is congruent to C mod n. For some integer h I can write B minus C equal to h into n. Okay, so I have to prove A is congruent to C mod n. Let me take what is A minus C. A minus C can be written as A minus B plus B minus C. I am adding and subtracting B, so that this is A minus B plus B minus C. What is A minus B? A minus B is Kn and B minus C is Hn. This is same as writing K plus H into N. In fact, it is nothing but N divides A minus C. Therefore, I can write A is congruent to C mod N. Let us look at the fourth property. If A is congruent to B mod N, is congruent to B mod N, and C is congruent to D mod N, then it says A plus C is congruent to B plus D mod N, B plus D mod N, and also AC is congruent to BD mod N. So for some integer k1 and k2, I'll write A minus B equal to k1n. For some integer k1, and C minus D equal to k2 into n for some integer k2. Okay, now to prove A plus C is congruent to B plus D, so I'll just take up A plus C minus B plus D. Okay, A plus C minus B plus D can be written as A minus B plus C minus D, right? A minus B is k1 into n and C minus D is k2 into n. So it's k1 plus k2 into n. It means n divides A plus C minus B plus D. So that the same as writing A plus C is congruent to B plus D mod n. Now have to prove the multiplication. That is AC is congruent to BD mod n. What is AC? A into C. A is nothing but B plus K1 into n. A minus B is K1 into n. A is B plus K1 into n. Similarly, C minus D is K2 into n. C is D plus K2 into n. The same thing I am applying here. AC is nothing but B plus K1 into n and C is D plus K2 into n. Same as writing BD plus BK2n plus DK1n plus K1 K2n into n. So I'll just rewrite it BD plus, I'll take up n common in these terms, BK2 DK1 plus K1 K2n into n. This is an integer, right? So AC equal to BD plus some integer times n. So AC minus BD is some integer times n. That means n divides AC minus BD. Therefore I can write AC is congruent to BD mod n. Okay, and the fifth property says if A is congruent to B mod n, then A plus C is congruent to B plus C mod n, and AC is congruent to BC mod n. This is same as the previous one, just we are using the term C is congruent to C mod n. I'm using this, and A is congruent to B mod n this, and I'm proving similar to the previous one. Okay, so I'm not going to do that. Let us look at the last property. This is quite interesting. If A is congruent to B mod n, then A power k is congruent to B power k mod n for any positive integer k. For any positive integer k. So this we are proving by induction. What happens is, I'll assume the result is true for k. Okay. When I take k equal to 1, there is no problem. A is congruent to B mod n. Okay. I'll assume this is true. Statement is true for fixed value of k. Okay. Fixed value k. Now I'm just taking A is congruent to B mod n, and I'm taking A power k is congruent. I've assumed that it is true for k. So A power k is congruent to B power k mod n. Okay. Now I know when two congruences are given, I can just multiply when they have same modular values. So I can just multiply A into A power k is B into B power k mod n. Now this is same as A power k plus 1 is congruent to B power k plus 1 modulo n. So result is true for all values of k. Hence I can say that A is congruent to B mod n implies A power k is congruent to B power k mod n. But is the converse also true? Means if I have A power k is congruent to B power k mod n, is it necessary to say A is congruent to B mod n for any value of k? Okay, k may be square, something like that. Is it true? In fact, it is not. Okay, suppose if I consider, say I have here the property since, suppose I have A is congruent to B mod n. Okay. Now, of course, it implies A power k is congruent to B power k mod n. I'll take k as 2. A square is congruent to B square mod n. Now, the other way is true always or not. In fact, it is not. You can check. Suppose I have values of A and B, C as A is 2, B is 3, and N is 5. Okay. In that case, A square is 4, B square is 9. I'm taking mod 5. They are congruent. Okay. 4 minus 9, that is minus 5. It is divisible by 5. So no problem. A square is congruent to B square mod n. But whether A is congruent to B mod n? No. 2 is not congruent to, in fact incongruent to 3 mod 5, right? It is not in 2 minus 3 is minus 1, which is not divisible by 5. So one way is correct. A is congruent to B mod n implies A power k is congruent to B power k mod n for any values of positive integer k. But the other way is not always true. Okay. Now let us solve few problems. Prove that 41 divides 2 power 20 minus 1. Usual division is quite different. Here we use the technique of congruency. Okay. This is 2 power 20 that can be written as 2 power 20. It can be written as 2 power 5 power 4. Okay. So what is 2 power 5? This is 32. Okay. And this 2 to the power 5 is congruent to minus 9 modulo 41. Right? I have to think of the smaller values of this. Okay, this B. It depends on this also, it depends on the power also. Okay, since you have got very small base, that is 2, it's quite easy to get. Now 2 to the power 5 whole power 4 gives me 2 to the power 20. So 2 power 5 raised to 4 is congruent to minus 9 raised to 4 mod 41. Okay. Now this is 2 power 20 is congruent to this minus 9 power 4. I'll write it as minus 9 square into minus 9 square. That is 81 into 81. Why I am writing like this is, see, I should get the smaller values over here so that say if I get 1 over here, then my answer way of getting the answer is quite easy. Okay, to get minus 1 over here, instead of multiplying these two, I can just check out with this 81 modulo 41. Okay, but the thing is, this 81 is congruent to minus 1 modulo 41, right? 81 is, when I take it over here, it becomes 82. 41 into 2 gives me 82, right? So this 81 is congruent to minus 1 mod 41. So 81 into 81 is congruent to minus 1 into minus 1 mod 41. Fact it is 81 square is congruent to minus 1 square mod 41. So here 81 square I have, this can be replaced by minus 1 square, that is 1 mod 41. So 2 to the power 20 minus 1 is congruent to 0 mod 41. When I am getting remainder as 0, that means that this n divides this. That implies 41 divides 2 to the power 20 minus 1. I have to get, usually such questions will be asked. We have to check out with the powers. Okay, and you have to get minimal values over here so that when I increase the powers on the left hand side, it's quite easy to calculate the values on the right hand side. See, similar problem, I'll take up one more, that is verify or check whether 89 divides 2 to the power 44 minus 1. I'll just tell you how to do. Okay, whether 89 divides 2 to the power 44 minus 1. Now you have got n value as a bigger value, that is 89. See, 2 to the power 44, you can write it as 2 power 11 into 4. Now see, you cannot differentiate this 44. You cannot write this 44 in powers of 2 in different ways. See, you can write 22 into 2, but getting 2 to power 22 is quite difficult. Okay, so among the many factorization, this is quite easier with respect to modulo 89. This we have to keep it in our mind. So now this 2 to the power 44 minus 1, I'm writing it as 2 power 11 whole power 4 minus 1 modulo 89. If I'm getting this as 0 mod 89, then I'm done. Okay, this 2 to the power 11 is congruent to what value of mod 89? In fact, this value is 1. I'll tell you how to get it. See, I have to consider those powers of 2 which when I divide by 89 should give me least remainder. Okay, see, in this case, if it is dividing this, then the remainder I should get it as 1. Okay, on which power of 2 when divided by 89 gives me remainder 1, that I have to check. Here the problem is I have modular n value as the large value. In this case it was quite easy because I had 41, so even the remainder is the big number, no issue, because on multiplying them I'm ending up by getting minus 1 as a remainder. Okay, in this case this is not so. If I consider 2 to the power 5, 2 to the power 11 as 2 to the power 5 into 2 to the power 5 into 2, then also I'm getting the remainder as big values only because of this n integer. So I have to check up for all the powers of 2. So this is the good value of powers of 2, so that I am getting a remainder as 1. In fact, 2 to the power 11, I can write it as, say, 2 to the power 7 into 2 to the power 4, suppose. Then 2 to the power 7 is 128 and this is 16. Then I'm getting this as 2048. Okay, 2 to the power 11 I'm getting as 2048. When I divide this by 89, I'm getting remainder as 1. Okay, so 2 to the power 11 is congruent to 1 mod 89. I repeat, 2 to the power 11 is congruent to 1 mod 89. I want 2 to the power 44, so 2 to the power 11 power 4, 1 power 4 mod 89, and which is congruent to 1 mod 89. So 89 divides 2 to the power 44 minus 1. Okay, similarly, one more you can check that you please do yourself, whether 97 divides 2 to the power 48 minus 1. Reminder, obtained by dividing the sum by 12, and the sum goes like this: 1 factorial plus 2 factorial plus 3 factorial dash dash plus 99 factorial plus 100 factorial. If this sum is divided by 12, then what is the remainder I am getting? I have to take that. Okay, 1 factorial, I hope you know what is factorial. 1 factorial is 1, 2 factorial is 2 into 1, that is 2,
3 factorial is 3 into 2 into 1, which is 6. Like that, 4 factorial is nothing but 24. Since I have got n value as 12, okay, I'm interested in taking 4 factorial. Now what happens? 4 factorial is 24. 24 is divisible by 12, so it is 0 mod 12. When I consider 5 factorial, okay, this 5 factorial can be written as 5 into 4 factorial. This 4 factorial is 0 mod 12, so 5 into, this is 5 into 0 mod 12, okay, so now this is nothing but 0 mod 12. Similarly, 6 factorial, I can write 6 into 5 factorial, which is 0 mod 12 again. So, for k equal to and greater than 4, k factorial is 0 mod 12, right? I'm sorry. Yeah. So, this whole sum now is reduced to 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial is 0, 0, 0, 0. So it is 0 mod 12. So it is reduced to this, and which is nothing but 9 mod 12. So remainder is 12. So the remainder is 12, that is 1 plus 2 plus 6, that is 9, and the remainder is 9. This whole sum is reduced to this, okay. When I consider mod 12, I'm getting 9 as a remainder.